Okay. Okay, so we ended the previous lecture by saying that the setup that we are working in is called a meta learning setup. Right? What do you understand when you hear the term meta learning? You're learning to? Okay, Suraj. No, no. You reuse the learning, and you said learn the hyperpriors. Any other definition of meta learning? Yes. Learning to learn, right? Meta learning. You're learning to learn. Where else have you heard the term meta? Where do we use the word meta? Metadata, meta reviews. What does metadata mean? Data about data. You're learning to learn, right? But what does learning to learn mean? If we know the definition, we know the connotation, but what does it mean? Let's go back to the example which we discussed last time, patient example, and see what the meta learning setup might be. Right? So let's assume that we have data for the first patient. We know the lung capacity and we know the lung capacity as a function of the weeks. Right? We have some data observation. We know more or less likely that it will be a linear downward trend. Right? Now we have data across multiple such participants. Right? So till this point it's clear there are multiple ways to solve this. One of the ways was what we studied in the previous class, which is hierarchical modeling, right? By which we are able to capture the relationship between the different tasks or the different participant. So what we'll say is that each task is the relationship, or each task corresponds to each patient, right? So for each patient we have some relationship between lung capacity and weeks, each of which we'll call it as a task, right? So we currently have n separate tasks, although there is some relationship between them, because that's what we exploited in the previous lecture, that we know that for all of them it will be a linear model. We assume that, and we also assume that the slopes and the intercept have something in common, right? They were coming in from the hyperpriors. Now we want to do the same thing in a more general setting. Right? The way we want to be using such models is that when we get a new patient, if we get a new patient, it's very likely, because we're telling it's a new patient, that they will have very less data available, right? So that data available would be, let's say, 2 points in this case, 3 points in this case, and somehow we want to be able to leverage these 2 points, which we will call as the context points, right? These are contextualizing your specific task, right? So if what do you observe between what is the difference between patient 1 and patient 10 given the data? Okay, Param. The slope seems to be different, right? So if you had a few data points from patient 1 and patient 10, can you tell which of them is which task? Probably by looking at the slope, right? The slopes are different, their intercepts are different. So the few context points should be able to tell you something about the task, right? And then that helps you to contextualize the problem, to contextualize the task. That is why they are known as the context points. So what we want to do is to use these context points as well as the learning across the different tasks, use all of this together to then make the prediction for some new data points for this new task, right? That is the broad problem. Have you used context specific tunings, context specific learning anywhere else? Sorry? Language models. Where in language models? Next word prediction. Okay. How have you used the specific context for next word prediction? The previous word you have seen, okay, that is a specific kind of a task itself. Okay, so let me give you a more realistic, more simpler example. I believe all of us are using ChatGPT, right? So how many of you have looked into ChatGPT? So let's see this question which I asked ChatGPT, and you tell me what you think about this. I asked explain linear regression, and it says that linear regression is a stats method used to model the relationship between this and this. It's a tool accountants sometimes use to analyze financial or economic data, and Imagine you're an accountant trying to understand how changes in one financial metric affect other, etc. So they're telling you which is likely to be a dependent and independent variable, the line of best fit, and the various kinds of things like y represents the dependent variable, example profit, x represents the input variable, example expenses, so on and so forth. Do you like this prediction? Do you like this answer which ChatGPT is giving you? It is very broad because the context that I had given it is this. I am based in the UK. I'm an accountant. I do not know much about computers. And I told ChatGPT to respond with, I like long text descriptions. I am poor in maths. So given this specific context, right, it is giving me a new answer. Right? So therefore, the context helps you understand, explain the new predictions. Right? So essentially, this task of ChatGPT is next word prediction like thing. Right? Now that is changing based on the context that I've given. Now, if I were to give it some other context, I will now change the context to I'm based in India. I'm a computer science faculty at a top research institute in India. I teach probabilistic machine learning. And I like Markdown, LaTeX. Give me maths and code over long text description, cut to the chase, and I don't like large answers. I've saved this. Let me copy the question. Let me ask again. In the context of probabilistic machine learning, linear regression can be extended to Bayesian linear regression where you incorporate uncertainty in the model parameters. Right? So it's become much more specific to the kinds of needs I was doing. It is telling me that Python, scikit-learn I can be using. It is directly giving me this equation, whereas previously it was not. Right? So this is also, you could think of it as meta learning in some sense. If you give in a specific context, you get context dependent fine-tuned answers, irrespective, in contrast to getting very generic answers. Any questions on this? I haven't yet told how to do this. Okay, let's look at another meta learning problem setup. I am given images. So this is an MNIST-like image. Now I'm writing as my specific task is that given XY, I want to learn the intensity. Is this a regression task or is this a classification task? Regression, right? So what we're saying is that you pick up X and Y here. So let's say X is 4, Y is 1. You want to learn the intensity. X is 1, Y is 4, X is 4, 4, 8, 8, so on and so forth. You want to learn the intensity. You want to learn the intensity mapping between this, right? So can you use such, and this functional mapping could be a neural network. Can you use, so can you be using such a network to complete an image? Can you do that? So we are given some points in this, let's say this is 8 cross 8 image. Out of the 64 XY pairs, you are given 32 XY pairs. Right? Using those 32 XY pairs, you learn this mapping between X and Y to the intensity. Right? Can you use that mapping of X and Y to intensity to then predict at unknown X and Y's? Right? If you do that, will you be able to complete the image? Yes. So therefore, you can use this kind of a problem setup for image completion. Now we can have those pixels missing at random, or we can have those pixels missing in a sequential, in some kind of structured way. Let's say if I remove the latter part of the image, that would be structured kind of missing. I can show you 2 or 3 ways in which people are trying to solve this problem. Right? So in this image, you are just given 15 XY pairs on which you have fine-tuned or context points. Right? And you are completing these images. You see that as you get more context points, the predictions will become better, obviously. Right? You are able to do the image completion much better. But this is showing where the images, the context that you are given is or the pixels which are missing at random. But we could have also had scenarios like this, where the latter part of the image is missing, and then you're trying to predict, right? But does everyone understand the problem setup broadly? Right? Each task is on a separate image, right? The mapping between x and y to pixel intensity, would it be same across each image, or would it be different across each image? It will be different, right? For some image, x and y corresponds to more density over one region, whereas for this other it responds to more density at some other region, right? So similarly, if you look at a task 8, if you give an x and y coordinate, it will probably try to learn the circular patterns. But if your task is a separate image, 4, it will learn a slightly different representation, functional mapping, right? So each of them, you can think of x and y. For each task, you could have thought of creating a separate neural network or a separate model. I'm just talking neural network in general, in specific cases to make it, that's where we use it a lot. The same thing which we could have done here. We could have fitted a separate model on a per patient basis. Previously, we did something like that in a pooled model, in the unpooled model. So similarly, we can build a mapping between x and y to intensity. For each image, you can do a separate thing. But then if for each image, if you're learning a separate model, how do you predict for a new image? Can we? So then you have to have something which is shared or it's learned across these different tasks. Right? And that is where the meta learning setup will again come into play. Right? So again, we'll have this new task. Given a few context points, I want to fill in the remaining part of the image.
How is it different from transfer learning?
So how is it different from transfer learning? Does anyone want to answer this question? Okay, there.
So in transfer learning, we just extract the features, but again we use recognition.
Okay, so there is saying that in transfer learning you're using a common network, a common feature extractor, and after the feature extractor you're just fine-tuning the latter part, right, which is specific to a task. Right? Here it's somewhat of a similar setup, but it's slightly different in the way that you're learning to learn. And when I show you the first kind of architecture which enables this, I think the question will automatically get answered. Other questions? Okay, let's look at one specific way in which we can do this meta learning. It is through a method or a model called a hypernetwork. So we will have the hypernetwork running in 2 different phases, during the training phase and during the testing phase. Let's go to the training phase first. So we are dividing the overall training data available to you for a specific task, right? For now, everything is, you should just see that I have given it for a single task. It will generalize to multiple tasks. You have a given task at hand, you have some training data available. Right? You assume some of it to be a context set and some of it to be a training data set. Right? So typically in supervised learning, we start with the training X train, we learn a network and we get a Y train. Right? Here what we'll have is, we'll start with and we'll have the same setup here also. We'll start with an X train. So let me show you the final product, and then you should just for a second assume. So don't look anything above where my pointer is currently. Look only below that. Given an X train, I have a neural network. I get a Y hat. I know the Y true. I can get the loss. I can back propagate and update the weights of the target network. Right? That is what we've been doing thus far in supervised learning. But none of this will help you to learn across tasks. If you were to create a separate target network per task, you can't predict for a new task. So therefore, we need something more. What we'll say is that we have a context set. It is a subset of the training data set. But here we are also looking at the Y. Right? Typically, while we are passing in any input to a neural network, we give only the X. only the features, but we don't give the y. But here we are storing both x and y's, and we also have the training data set. Right? I've purposely written down the shape so that we are very clear. So x context is nc cross d, and y is context is nc cross 1. We concatenate these two, this matrix and this vector to get a context set which is of size nc cross d cross 1, nc times d cross 1, right? Now we start with this context set which is nc cross d plus 1. We pass it to a neural network which is a hypernetwork, and we'll get an output nc cross k. Why do we get an output nc cross k from this network? K is not the number of, for what? K the number
for the neural network, for the target
So
network.
we'll come to that later. The question is, why are we getting nc cross k shape? No, k is not the number of tasks. It is some representation, right? So we don't need to care about that. I was more asking why we're getting the nc number. Because if we're doing a forward pass on nc samples, we'll get nc cross something, right? Some number, which is what is the output, this is the number of output nodes in the final layer, right? So here we have nc cross k. Now, what you want to do is, out of the context set that you have given, you want to then aggregate it, because you want to get something which is, okay, let me show you. So we aggregate it first, we get a vector of length k, right? Aggregate it across the number of context points. We get a vector of length k. We reshape this into certain weights and biases matrix, right? So let's say k is 1000. You reshape that into a 10 cross 10 matrix, 100 points go there, you get 100 biases. The next layer is maybe a 20 cross 20 or something like that, right? So basically you have to start with this number k, and you have to reshape this into w's and b's, which are the weights of the target network, right? Any question on this? So these are the weights of the target network. Now you pass the training data to this target network, right? The target network is now parameterized by the w's and b's, right? Once you do this, you will get a y hat, which is the prediction. You know the ground truth, which is y true. You can compute the loss, right? Now, where do you want to do the back propagation into? What do you want to update? Why would you want to update the target network? You're setting the weights of the target network via the hypernet. So you're setting it explicitly. You don't want to be updating it. You want to be updating the weights of the hypernetwork. You update the weights of the hypernetwork this way. Questions on this? We'll show in the code example how we set these weights. Yes.
Like, I understand the reshaping part.
Mm-hmm.
It makes more sense to have like another fully connected layer.
Mm-hmm.
To learn W1, V1, maybe the reshaping is kind of like a additional constraint on the
Okay. Mm-hmm.
architecture.
Mm-hmm.
So can we have another fully connected layer between the hypernetwork and
You can have that, right? You can do that explicitly, but it's assumed that this will have the same effect. Like through the back propagation, the weights will be adjusted in a way which will make it similar to what you're trying to do. Like there are a lot of moving pieces here, right? So one of the moving piece which may cause you some confusion or may be harder to grasp is that I started with NC cross context set of size NC, right? But I suddenly aggregated it into a vector of length k, right? Now give it context set 1 or context set 2, it will just do some aggregations and it's still working out, right? So there's a bit of magic which goes on here, but you have to essentially think of it as that it's trying to capture the essential part of the context set which defines the task, right? So the weights of the target network become this forward pass output of the context set once it's trained. right? So it's, yes, Harsh.
And we have something like add this context set as information for each input and then train individually for that input. It would be like, for example, the context that you put, I am a consultant in UK, I am an accountant. Adding that for every prompt that we are giving in the bracket, so it will still give kind of similar result.
I fully didn't get that, but I think what you're getting is another way to solve this problem, and I'll show that. We'll look at that in 5 minutes. That is another different way of doing this meta learning. Right? But broadly, do we understand this? Right?
Sir, are we, so just a doubt that the Hypernet is predicting what target net should be.
Yes, the hypernet is predicting what the target net should be. So think of this as I give you a context at runtime. Right? I go back. Let me go back here. Let's go back over here. Right? I give this context. So test time. Let's just think of test time. I give these two context points to a neural network, and let's assume that my target network is a linear regression model. Right? Now it will tell you the weights and biases, or it will tell you the slope and the intercept. You've learned that for every different task, given a few context points. Other questions? No question?
So in this meta architecture, so we have n sequence cross scale, number of context for cross scale. Then these are latent space representation dimension. So that dimension is just converted into the model parameter. So
Yes.
that target net layer, they have a large number of parameters. So it's up to us.
Yes.
But so then K is the latent space representation. So there is a cursor dimensionality also. So then how can we touch it?
Right. So Vipul is asking that if we have a huge target network, we will have a hard time because we will have a lots of weights and biases, and you're trying to predict a very large representation. I think in practice, people generally don't want to be using a very large target network, right? But you can still use it. I am not sure what people have done a lot in practice. Like, essentially, it should still work out because you're just parameterizing the target network that way. It's not, you're not directly comparing the two different context sets being learned, or the two different representations being learned, where the cursor dimensionality plays a lot more sense. You are just parameterizing a neural network. Other questions? Okay. So we looked at how the backpropagation will update the weights of the hypernetwork, and it will not change anything in the target network implicitly. Okay, what do we do in the testing phase? We get a context set from the target task, right, which is nc cross d plus 1. We pass it to the hypernetwork. It predicts the weight of the target network. I given my test input and t cross d to it, and I predict my y hat. That is it. So let's first see this in implementation, this in code, and then we'll come on to the other specific method to do this, where we have an encoder-decoder architecture. Right? Here we are directly predicting the weights of the target network. Right? The context tells how the target network should behave. In the other way, we will not do this. We will expand the feature space. This sometimes happens. This has happened for you also. How do you resolve this? I typically uninstall the extensions and okay, anyway, I think we can still go through the code. I think I have all the output stored. Okay. Let's go through the code. So now if you remember the code from the previous class, I am essentially using that code to generate the data for this class. I have a mu alpha, sigma alpha, mu beta, sigma beta, and I have 11 tasks. And I've specified the distributions. I'm getting mu alpha samples, sigma alpha samples, mu beta, sigma beta samples. And I get my alpha, beta, sigma. Right? My alpha is normal with mu alpha samples, sigma alpha samples, so on and so forth. And my true function for each of the tasks is alpha phi plus beta phi into x linear length space. I add noise to each of my observations. So it becomes each of my true functional values. It's a normal with the true function value with sigma phi. So another thing you could see is that we can put these Unicode characters. So that way you get the math as close as possible. That way you get the code as possible to the math. And I'm doing a bit of normalization just for making the tasks, making the neural network learn better. So you can see that these are the 10 tasks for which I have some data. I have quite varying tasks. If you look at the alphas and the betas and the sigmas. So the alphas is from -2 to +3 point. So this is also -7.73, -1.09. Right? So you learn different tasks. I mean, this is the data across different tasks. And after that, I just plotted it normalized. Right? Now you are given a new task for which I have only a few context points available. Right? In this case, I'm just showing 5 context points available, and I want to be able to predict the true function or the values of the true function at any given x. Right? So this is the setup broadly. I am also showing that in order to train such a network, for each of the tasks for which you already have all the data, you will divide the trained data into train and context. Right. I will be using, in this case, I've used about 50%. I've used 50% of the data for training and 50% as context across each of them. This is another picture I picked up from a good video, but this is essentially what we are doing, right? The meta input is a context set, which you pass to the hypernetwork, which helps you set the weight for the target network. You give in the true input, or the target, or the test input, and you predict y hat. The loss function is there, the gradient updates the weights of the hypernetwork. The code is quite simple. I am defining a hypernet as a sequential linear activation and linear, right? So my why do you think it's the first layer is 2,64? Why do we have this number 2? Because the hypernet, what does the hypernet take as an input? The context set, the hypernet, not the target network. The hypernetwork takes as input the context set. But why is the context set having a size 2? X and Y. Right? So X and Y, both of them are 1D vectors. So the size of this becomes 2, and the hidden units is 64. I put an activation, and then my output is 64 cross 2. So my final output, my last layer is 64 cross 2. Why do I have 2 in the final layer? because I want to have two parameters in my target network, which you can see here. Target network is torch.nn.linear 1, 1. Right? But if it's 1, 1, why does it have two parameters? Weight and bias, right? So this is the whole setup in terms of specifying the hypernet and the target net. Now, just to make it very clear how we go about this, let's pick up task 0. This was task 0. We have train and context here. We will use the first 50% of the data for training, the last 50% for, okay, the context is 50% of the training data, and the last 50% is used as the target or / training data. I will concatenate the xc and the yc, right? So xc dot view minus 1, 1 and yc dot view 1 minus 1, 1 across the first dimension. And if I look at the shapes of each of them, you can very clearly verify that my context shape is 25 cross 2, 25 and 25. So my context set has dimensionality 2 eventually. This will go into my hypernet now. And I'll show this in process. Hyper out equal to hypernet and the context as the input. If I look at the output of this, I get 25, 2. Now I want to aggregate into a vector of length 2. So I will take the mean across the first dimension. So that is what I'm doing. Weights equal to hyper out dot mean along the 0th dimension. Weights are of shape 2. Now this is where we need to be little careful about how to set the weights for the target network. We have obtained the weights from the hypernet network, but setting the weights is not as trivial. Like you need to do something sophisticated. Here I'm showing you a few ways in which you can do, but none of these work in the final case, right? Because you want to be able to do it in a way which preserves the automatic gradient computations. You want to preserve the computation graph. So I can create a target network as nn.linear 1, 1. I can set the weight.data, bias.data. The first element of my weights, I put it in the weight of target network, and the second element I put in the bias. You can do all of these things. But what you want to be doing is, I'll show in just 1 second. And finally, you want to be using the target network, pass in the train points, only the x of it, and get the ypred and compute the loss between ypred and the y-true. Let's see this in action in a fully working example. I am using a single task at this point of time. I define the same hypernetwork as before. I define a simple target network. I have an optimizer which is going to operate on the parameters of the hypernet, not on the target net. I specify my loss to mean squared error. I get the state dictionary corresponding to the target net. Right? The state dictionary corresponds to the weights and biases. Right? Then in the training loop, I zero out the gradients. I do the forward pass on the context set. Right? I get the weights equal to hyperout.mean. And this is the step which preserves the working of the automatic gradient. New dict dot update with the weights and biases. Right? The weights I'm obtaining via taking the hyper out and taking the mean out. And then I'm calling the functional call method, which I showed in the previous notebook on Laplace approximation method of getting uncertainty out of neural networks. So I do a functional call on the target network with the weights on this input, and I get the Y prediction. I compute the loss, call the step method, and then on this specific task on which I trained, I'm showing that I'm able to learn well. Right? But this was nothing sophisticated. Right? We didn't need meta learning for this. Now, if I have to change this code to do meta learning, what all changes do I need in code? Anyone? What changes do we need? Okay. Yeah. Right. So you'd want to be not just giving data across one task while optimizing the hypernetwork. That is no use. So you want to be giving various tasks. There are multiple ways to do it. I am just putting a loop over it. Right. So the first part is the same. My hypernet is this linear activation linear. My optimizer is over the hypernet's parameters. My new dict is I'm getting the current state of weights and biases. Right. Then my training loop. In my training loop, I loop over each task. I had 10 tasks. I define the context and the target sets for each of the task as roughly 50-50. I obtain the context vector. Now, this important thing is that this is done on a per task basis, right? So for every task, I define the context vector, which is concatenation of x and y. So it becomes d plus 1 dimensional. I zero out the gradient. I get the Hypernetworks output from that. I update my dictionary to set the weights of the target network, and then I do the functional call to get the y hat. And I know my y true for this specific task for these specific training inputs that I'm giving, xt inputs I'm getting. I call l dot backward, and every few epochs I'm printing it. Right. So it's not a very sophisticated piece of code if we understand broadly what we are trying to do. And then we can predict, having learned, we can try to predict on all the tasks. So when we're doing the prediction, now we just need to get the context set. The context defines the weights for the specific task at hand. Once we get that specific, so see this, we loop over the tasks. For every task, we get some context. Once we have the context, we pass that context to the hypernet. We get the weights, which we then reshape and put it in the target net. So effectively, now we have, through this forward pass, we have obtained a new target network. We pass our inputs to that target net, which we've obtained, and we get the Vipred. And this is how we can see the fitting across the different tasks. It seems to have done a reasonable job here. Yes.
Yeah, I think there's a problem because if we are trying to make a network weights learn across different tasks, then we'll need, and the training samples are very low. The loss will fluctuate very high because first task it sees like I have to learn something like this. Then second time it's completely involved. So we'll need a very large number of epochs to train.
Here we didn't need a large number of epochs. This setup was simple because I had chosen the tasks in a specific way. It may take a large number of epochs. That's fair. I mean, that we'll have to see on a per task basis, per problem setup basis, and see what works where. But this whole formulation I wanted to show that like we can predict for different kinds of tasks given a small set of inputs as a context. Other questions? And then if you want to predict for a new task, you again create a context vector for that new task. You will be given a context vector for that task, and you just do the same thing. You pass that to the hypernetwork, you get the weights of the new network, you do the functional call to predict from that network, and this is the prediction on this specific task. It given only 5 context points, which are shown in this with this red dots. Oh, the colors of the legend are the other way around, they're flipped. The context is just 5 points which are used, and then we're able to predict quite well on this task. Okay, other questions on this? Yes.
In practice, how do we decide what level do we go to meta? How do we decide the tasks basically, which can be learned in a meta?
Okay, the question is, how do we decide what kind of, like, how do we decide what is a task? Any thoughts on that? So sometimes this question is answered very simply if you look at, for example, the two kinds of tasks that we had seen. Right, so here it's in this specific task, it's very clear that you will have to learn a separate neural network per image that you have given, per image class, per image that you have given. So here it's a very good setting to use meta learning, right? So that given a new context set of points, you can predict for a new for the new task at hand. Right? Here it was fairly easy. The previous one also, you think of it as whenever you have the setting where you have certain kinds of tasks, or like patients example we had, we know that there is some amount of relationship between them. Like generally, you would expect that the lung capacity will reduce over time. We know that, and we will have the for any new set of patient or any new task, we will only be able to get a few data points. So this is the problem setup where generally meta learning becomes useful. Slightly related kind of environment across the different tasks. At the same time, for the new task, we will have a small set of data only available.
So, for example, in this task, if I would have just black and white pixels and the color, then it becomes a completely different task which cannot be meta.
So then that will become, so Param's question is that if uh, we have some black and white images and some grayscale images. So there we, firstly you need to see that this specific model that we're looking into goes from xy to a single number grayscale, whereas the other task that you're talking about goes from x and y to RGB. Right? So the tasks themselves are not having the same input, same output. Right? But you could again think of smart ways in which you can manipulate these things and use them across meta learning setup. Like people have been using meta learning across varieties of tasks, right? So people have also been using it for, let's say, weather forecasting. You could think of each image, each radar image, as a separate task, right? And then you're trying to learn a forecasting setup between them. So a bunch of such tasks have been done. Other questions?
So can you take two different problems as a task, so to make it a model robots? So for example, this one can be classification and one can be regression problem in the same data set.
So Vipul says that can we use um, so people are generally, there are two ways in which people try to attack such problems. One are the multitask kind of models, and here we're talking in general about meta learning, learning to learn, right? In multitask also you can predict multiple things. For example, for an image, you could, one of the tasks could be just classification, whether it's a cat or a dog. The other task could be localization. You're trying to localize the ears, or the other could be object counting, right? So all of them are the examples of the different tasks in that specific context. Here I'm talking about the setup where we have related tasks, right? Where we are looking into the same inputs, same outputs, right? And we are trying to see that if we have very less data available for a new task at hand, then what we can do.
So how are we defining the number of tasks and the different tasks?
We are defining the number of tasks in this case. For example, for the patient example, each patient is a new task. For the image example, each image is a new task. So we've looked at one specific way to solve this problem. Now we've looked at hypernets. Let's look at another way to solve this problem, which is through something known as a neural process. Although we'll not be looking at the stochastic part of this neural process for now, which is also very interesting. But we'll be looking at a different architecture sort of which is commonly used in the neural process world. Again, we have the same context set, NC cross D plus 1. We have the same train / target available. Now we're talking about the training phase, and train cross D. We pass the context set to an encoder, which gives us a representation NC cross K. Now we are explicitly calling it a representation. We will do the aggregation to get a 1 cross K. Typically people do mean aggregation. Right? Why might people prefer mean over sum? Yes, you could give a context set of size 1, 10, 50, 100, 500. So it depends. The sum will become a function of that, whereas the mean is going to be independent. Now, previously we had set this k weights, k numbers that we had learned as the weights of the target network, right? But here we don't call it a hypernet target net architecture. We call it an encoder decoder architecture. Encoder takes an input, gives it a representation. Right? We have the train, which is n cross d, and now we have an aggregate function, aggregation representation that we've learned, which is 1 cross k. You concatenate these to get n train cross d plus k. Right? So think of this setup as that the encoder helps you to learn new features which are going to help you in solving that problem for that specific task. Right? Previously, the hypernet helped you to learn the weights. Now the encoder is helping to learn additional features which become helpful in solving that particular task. Right? Now this new input that we have, n cross d plus k features, d plus k features that now you have, we pass it to a decoder, which could be again another neural network, which will then give us a y hat. Now we have the y hat, we have the y true, which is n cross 1. We compute the loss. Now what will backpropagation do? Previously we were updating the hypernetwork. What should backprop now update? Okay, how many say encoder? So I want answers from everyone. How many say encoder? Okay, 3. How many say decoder? How many say both? Okay, we need to be updating both. That is the difference in the problem setup. We need to be looking at the encoder, which gives you some different representation. You want to be improving the representations that you're learning from the context set, as well as when you pass in that additional representation features to the decoder, you want to be able to get more better task specific performances. So the back propagation will go backwards to both these paths and update the weights of the encoder and the decoder. Right? So we've looked at 2 different architectures to solve the same problem. Any questions on this method?
So what type of task will have context set? Like, because that is the different part. Like, with the normal where we are guessing the number, there we only had the image. So
I am not getting you.
So like as an input, now we should also have some of the output points.
So the context set means XY pairs. For a new task, if you don't have context, you are helpless. You need to have some small context set available for a new task. That is the whole formulation here. We will always assume some context is available. Because the context only, if without the context, you cannot make prediction for that specific task. We backpropagate. At the test time, we do pretty much the same. We start with the context set, pass it to the encoder, learn the new features, k-dimensional features corresponding to this task. We append those features to the target inputs, t-dimensional target inputs, to get a d plus k-dimensional input representation. We pass it to the decoder and get a y hat. Yes.
My question was, so the context set and the xt correspond to the same task.
The context set and the xt at any given point of time will be from the same task.
So what is the advantage? Because even for the new task,
no, that is a wrong assumption. For a new task, we require a small amount of context set, and we'll see some results. That is the whole point. If we require a lot of context set, large context set from a new task, no point doing the meta learning. Then we should just learn a task specific model.
Okay, so XT, only small amount of XT is also required.
So XT is at the time of testing, the XT is the target, it's the test points, right? So again, go back to these slides. Neural processes at the time of training, we have X train. At the time of training for a given task, we need X train and corresponding Y train, right? Because we want to do the back propagation, we need the Y true as well as the X train and the context set, right? So think of this as at the time of training for a given task, you need to have, this is the entire training data available to you. You have divided the training data into context and train, and in the decoder, you're only passing the train inputs along with the representation you're learning. At the time of testing, you only need a small amount of context set. This is all the points, target slash test is all the points on which you want to predict.
For the new task, X train will be large amount.
For new task, we don't have X train. We just have context set. We don't have the train data available. We have a context set available. If we go back to the notebooks I shared, right? So now look at this. If you were doing an individual model prediction, right? If you were learning an individual model, do you think you'll be able to use this context to predict this image? No, right? You need to be able to do meta learning. You have generally learned that what kinds of pixels will correspond to what kinds of outputs across varieties of tasks. You've gained some learning to learn capabilities. Right? You can again see that as the context points will increase, the predictions will obviously improve. So there are two different papers which I'm showing. This paper is showing for MNIST as well as the celeb images. Right. Given this context points, you're able to generate these images. As the context points increase, the predictions will obviously improve. The training data would be done in the same way as we showed. Let's say you have 100 images, right? For each image, you know the X, Y, and the intensity values, right? For each image, you learn a separate, you could have learned a separate function if you were to do it that way, which maps from XY to intensity. So you break this XY comma the pixel value, I mean the pixel location comma the pixel value into target, into context and training. Right? You do that for each image, and for a test task, for a new task, you'll only be given a new some specific context points, and you want to predict the result.
So 4 was not there in the training data.
For this specific 4 was not there. It depends on what kind of a problem you're trying to solve. In the MNIST example, I think what they're trying to do is they're using the entire MNIST data. They have seen 4s previously also. But you can have another variation of the problem where you have not seen 4s. Such. No. The new task only requires the context points. The context points are pairs of X and Y's. So it's the terminology which I want you to pick up carefully. Training is like we saw, right, in the code. Training, so okay, let me go back to the architecture only. The training data is only consisting of the input features that is sent to the target network, and you obtain the y hat. The context is a concatenation of both the x's and y's, right? But during when we saw in the code, during the training phase, for each task we are overall just given a train set, right? We divide ourselves the training data set into train and context. Right? For a new task, only the context, which is xy pairs, are given to. Target test is the new set of points on which you want to predict. New set of inputs on which you want to predict. If you go back to the image example, this is my context set, 4 points. My target is all the 60 remaining points. Right? I don't have y's corresponding to them. Okay. Any other questions?
But if I relate this to the hierarchical models we were trying to go on the level where you have the new and I learn for this.
Yes.
How do we relate this latent representation?
So there are two ways in which we have seen, right? So in one of them, you learn the networks directly, right? So you've learned the W's and biases, right? Think of this as you have learned the mu's. You have been able to get the mu and the mu alpha and the mu beta for the specific task. So that is the setup with this, how it's related. In the neural process, the feature itself are expanded, right? So it's not directly comparable to that example because the feature space itself is expanded, and then you're doing a simple linear, let's say a simple linear model on that.
Can't we use similar setup to predict the posterior like we used earlier? So we don't have to do that Laplace approximation.
I have no clue on what you're asking me.
For example, we are predicting the weights of the network.
We are predicting the weights of our network, and
Or some method we were trying to predict the posterior. What if we're trying to predict the posterior directly using this method? Instead of weights, we're predicting the posterior.
the posterior is a distribution.
Yeah, so posterior means the new and covariance.
Right. You are trying to predict. You will typically want to. So you'll typically not want to predict the covariance matrix anytime. You want to be looking at the square root of that, which is Cholesky factors. Right? But for things you have closed form expressions clearly available, why do you want to backpropagate and learn them? It's a much simpler problem to directly use Bayesian linear regression. Neural networks and stuff. What do you want to do? I still don't get it fully. So in last layer approximation, you're putting in certain distribution over the weights, right? If you're not putting any distribution of the weights, how can you learn the posterior over them? You need to put a prior, and you need to get a posterior, and then you are making an approximation over that. Like if you don't put any prior, you have not made them stochastic. You can't really be learning anything which is stochastic. You need to introduce a stochastic. So this is the downside of hypernets and neural processes. And because of the flexibility, I think sometimes we can think they can solve everything. Wherever closed form of solution is available, we should prefer that. But all of the questions you're raising are interesting. You should try to think through them, and perhaps you'll get a sense of which will work, will not work. Because you can have a lot of such configurations, right? Here you're concatenating. But you could also do an encoder which does this concatenation, give it to the train, and get a better representation. As well as you can use the same context with a hypernetwork to learn the weights, right? And then pass it, and that becomes your decoder, for example, right? Now the back propagation will flow in very complex ways. You could do all of those new novel things that way. So we can quickly go through the code for the decoder also to see how it works. Sorry, neural processes also. The important thing again, I'm showing only a limited case of neural processes. I'm not showing the full neural process. So we create an encoder. Okay, why is the encoder of this specific shape? Can someone tell? Linear 2, 128, then an activation, and then another linear. Why do we have this number 2? Firstly, nope, not weights and bias. X and Y. The context is an input to the encoder, X and Y. X is one dimensional, Y is one dimensional. You get this 2. Why this number 128? Could have been any number. Then 128 and 128. And my decoder, why is it size 128 plus 1? As in 1 is the input, 1 corresponds to the input dimensional X, 128 corresponds to the representation that you have learned for that specific context. Right? So you are expanding the feature space from 1 to 129 in this case, and the output is 128. Sorry, then you have a ReLU, then you have, finally you have an output 1. Why do you have an output 1? Because Y is of, it's a vector of size 1. No, this 2 is not. What is the input? What input do you pass to the encoder? Context set. Context set is of size. X is of dimension 1. Y is of dimension 1. So therefore the context side is of dimension 2. We pass 2-dimensional input to the context, to the encoder, and you get 128-dimensional output. To the decoder, you pass in 129-dimensional input. One of that 129 is coming from the X. The remaining 128 are coming from the representation that you've learned. So if we go back, NC cross D plus 1, right? D was 1, D-dimensional input, 1 is coming from the Y. So therefore the context set is of NC cross 2. Therefore the encoder has to start with 2 comma something. Finally the encoder gives you NC comma K. In our case the K is 128. NC comma 128, you aggregate it, you get 1 cross 128 or 128 length vector. NC n train comma D, D was 1. So you have 1 and 128, concatenate, you get n comma 129, which you pass into the decoder. The decoder has to finally give an output of size 1. So again, I'm just walking over the entire process. You get the context, which is a concatenation of X and Y. You pass that context to the encoder to get a representation. To get this representation NC cross K. You pass the context to the encoder to get a representation. You aggregate that representation dot mean. You look at the representation shape 1 comma 128, just 1 comma K. You get the target representation, which is representation dot repeat. So I'm calling this repeat function because I want to be repeating this representation across all of the n examples. So I want to go from, so this is 1 cross K and this is n cross D. I want to basically get n cross D plus K. I won't be having only 1 cross D plus K. So therefore I repeat this vector n times. I get n cross K and n cross D, concatenate them, get n cross D plus K. Join target X equal to concatenation of target representation and the input X. You will get 25 comma 129. 25 is n, 129 is the representation, 128 plus 1. I pass the representation, the joint input to the decoder to get a prediction of shape n comma 1. So at least the shapes are matching up, and then this is the optimization loop. You are now, if importantly, you are optimizing over the encoder parameters as well as over the decoder parameters. Unlike the hypernetwork, where we are only looking at the hypernet parameters, we in the forward pass get the context, pass it input, pass it as an input to the encoder, get the representation, aggregate the representation, concatenate to get the new input to the decoder, pass the new input to the decoder, get the Y prediction, compute the loss, backpropagate. And I am not showing the numbers, the results here. we can still do some improvements in the notebook. But this is the main loop in this. Okay, other questions? Yes, Suraj.
Finding it difficult to distinguish between class and a task.
The
Or class and task.
okay. So class and a task. Let's talk about a classification problem, right? Where we will talk about a classification. Let's say we are talking about dogs and cats, right? So that is a classification problem. Given, so firstly, let's talk about a supervised example, right? In a supervised learning examples, you will have examples of input images and the corresponding Ys for both the classes, right? That is a classification supervised learning setup. Now the task, you will have to be defining the task in a separate method, right? So firstly, I'm specifically talking about regression because the formulation is quite easy here, right? So we have looked into two examples of for regression. You have looked into when you are given different patients, right? Your different task is each patient is a different task, right? And you want to predict on a new patient. You want to look at the small set of context points given to you. Okay. Is this much clear?
For this example, it was same. For the numbers example, like
For the which example?
number example.
Number example. Okay.
So
The number example is a regression problem. It's not a classification problem at this point. Yes.
So there you said that maybe for MNIST they are training the entire MNIST.
They could have, for MNIST, they could have used a small, they could have used some number of images. Each image you could think of as a task, right? For each image, you're learning this functional mapping between the pixel indices to the pixel values. Now, given a new image for which you know only a small set of context points, you want to be able to complete that image. Yes.
So you said that
X and Y are?
like the context points are fine, but there are multiple context points. So will the training happen for each context?
Okay, good, good. I was hoping this question will come. So, if I change the context point, will I learn a different? Let's talk about a test time. Right? If I give you a context length of, if I give you a context of this context versus this context versus this context, firstly, do you see a difference? You see a difference, right? So the size of the context set definitely matters. Will the context, not the size, this I give the same context size, but I give you different context. Will that also change your output? Yes. As an example, if we go to these examples, for let's imagine that you remove 50% of the images, 50% of the pixels, either missing at random or in structured missing. Will you get a different output? Yes. So the specific way in which you give the context also matters. Now coming back to Kalish's question on how to do the training. So typically during training, you don't want to be using the same context points and the train points across all the iterations. For each iteration, you want to be randomly splitting your training data into train and context. Right. Now there will be another question, which is how much to give for train, how much to give for context. Do that in the next assignment. We'll give you a question like that.
So one more question, common which is that how to choose the context set, keeping the number of context sets same. So can we choose these points to tell me the context, a better context?
So the question is how to choose a better context. Typically, you just do that randomly. Right? That will turn out to be okay. Until unless as a part of the training, you are not introducing the specific bias of only certain context being given, random context should generally work out okay. And think of it as in a real life scenario, you will never have a choice over the context. That is what is made available to you. For a new patient, you can't tell that you should have come 1 week earlier and given me a lung health reading, right? Because my model will not work well. Can't do that. During training, it's up to you. Like you want to be trying out different variations, combinations. Okay, so Vipul is saying that can we choose You want to choose context where you're highly certain or the train points?
Yes, the points can be highly certain. So that's the points that can be highly certain or highly uncertain. We have to show, and then set the answer context. So because our hypernet is dependent on this.
Okay.
So that a critical point of critical architecture is dependent on this.
Yeah, I don't know how you'll be able to address all the questions of what you're trying to raise with like very specific context set designs. Typically in practice, this random works out okay. So one question which I typically ask whenever some students are working on this kind of a setup is, can you you fix the architecture, now you vary the different context sets, and you tell me if there is a huge variation in my output or not. Another thing which I even been thinking is that assuming that we have access to infinite to a large context, can we choose the context based on the target that we want to give? Like, we can think of those things. There are a lot of such variations which are possible. We have looked at two simpler approaches. Like there are attentional based methods also, which will then look at the interactions between the target as well as the context. So you have such variations in attention neural processes. Okay, any other question? Okay, thank you. We will meet after the break. We will try and send you the assignment during the break so that you get a lead time. After the break, you'll see that the semester will get very heavy. Like you will probably know that.